Hello everyone, welcome to yet another lecture of estimation and detection theory. So here we would be starting a new criteria. Okay, so in the last three lectures we have described the NP detection criteria, where only the class conditional PDF of a particular observation of a set of observations were given. Now there are both pros and cons to it. The pro is that a very simple detector can be made out of it, which can also be claimed to be the most efficient detector in a certain scenario. But the downside of it is that it lacks more information. Okay, for example, if we make a system where we tell that if you do it wrong, you have a charge to incur. If we add a parameter called as cost is basically we are we are giving a parameter that would be higher for any mistake that is made by the system. So if there is a cost associated with the system, if we introduce this parameter as a novel parameter for that system, we can design a more complicated, a little sophisticated detector, encompassing more information and more efficiency in terms of what we expect out of it. Okay. So specifically here, we want to make a new kind of detector. Why? Because we have access to new information. Okay. So first one is cost. We set the cost that is associated with making a particular decision. This will form a very important criteria to build up this decision criteria. Also, we are given the prior probability. We were not given the prior probability before. Okay, so prior probability, as you know, is just the probability of an event without any kind of condition, just like that. Okay, if there are n1 instances of one event and n2 instances of another event, so that particular event, the prior probability will be n1 by n1 plus n2, a very simple expression for that. So in this specific place, we are given both cost and prior probability along with class conditional PDF. Okay. Now, when we have prior probability and class conditional PDF, there is a magic we can work out. This magic, the key to this magic was given by Thomas Bayes 300 years back. He was a statistician, a philosopher. So he worked a lot on developing statistics, and he is the father of Bayes theorem, which reigns the world. Even in machine learning, if you see, the basic mathematics are all based on Bayes theorem. If you don't understand Bayes theorem, you will miss a large chunk of the understanding of the concept of various concepts of statistics and how it is applied. So very interestingly, Thomas Bayes, when he described or when he discovered this, he considered it not to be of much importance, and he left it just like that. He did not even take much notice of it. Thankfully, another guy in the name of Richard Price, he like quite some time after Bayes was dead, Richard Price was just browsing through the catalogs, browsing through the volumes of work done by Bayes, and he accidentally hit upon this rule. He immediately recognized the significance of this and published this. And the ethical credibility of Richard Price is such that we don't even know his name now. He actually rediscovered this from the notebooks, and he gave total credit to Bayes. This is how the ethics of any researcher or any scientist or anyone of the present age as well as for the future should be. There's an ideal example of how a scientific mind is. So Thomas Bayes is accredited to this beautiful, simple and elegant formula where we can find out the posterior probability given a data, given an observation, just with the class conditional probability and the prior. Okay. The total probability remains more or less the same for a given set of hypothesis here or classes, whatever you call it here, simply because we are summing up the product of the class conditional probability and prior for each of the classes. So this forms a very central piece in the concept of probability as well as statistics. You might want to check this out. There are very good lectures available in YouTube, I guess. One channel is 3 Blue 1 Brown, 3B 1B. They have described Bayes rule from a very different perspective, as they do. The illustrations are very beautiful. There are also videos of Veritasium. Veritasium is another great channel for science communication. You can find out the Bayes rule. Why I emphasize on Bayes rule so much is the significance and the span of Bayes rule is so wide, starting from the machine learning domains today, the developing the mathematics from scratch, to a lot of statistical phenomena worldwide. This forms the stamp equation that is used to derive those things. So a good feeling of Bayes rule is absolutely necessary to proceed forward. I would say that you have to have a clarity on how this rule works and why this works. The explanation is very simple yet elegant. Okay, all right. So for example, we have an observation X. Okay, we have an observation X, and there are two classes, say H1 and H0. Now, how do I decide whether that observation belongs to class H1 or class H0? It is by Bayes rule. How? See, given an observation X, the probability of it belongs to H1, class H1, if that is more than the probability of the given data belonging to class H0, then we can say that it belongs to class H1. Okay. Otherwise, it belongs to class H0. Okay. As simple as this. Now, the moment you have a posterior probability where we are trying to find the probability that given an observation X, it belongs to a particular class, we can use the Bayes rule in terms of, in simple terms of the prior and the class conditional probability. Okay. Now, if this product, this simple product, because this cancels up the denominator, as I said, it remains constant throughout. If this is greater than the probability of in H0, it belongs to class H1, otherwise H0. Okay. So this is the particular idea that we will be taking forward to build up this particular decision criteria. Okay, so you should be very clear in your mind. In the last time where we had built up NP criteria, it was simply because we had only one information, that is the class conditional PDF for each respective class. We are discussing a binary detection scenario now, so we will be having only two hypotheses, H1 and H0. Okay, we will be continuing until I tell anything specific. We shall be continuing our assumption with the binary detection scenario. Here we have costs and prior probabilities as an extra piece of information that is available to us. Okay, as I said, the costs are important when we specifically want to attach a weight to right decisions and attach a penalty to wrong decisions. Okay, more cost should be incurred to take wrong decisions. Okay, anyway, coming to the formalization. But before that, let us discuss the four scenarios of detection that we have. Okay, so you see, there can be four particular scenarios in this binary class problem. First one is under hypothesis H0. Okay, under hypothesis H0, there can be two conditions. So under hypothesis H0 means we have transmitted H0, but we have detected H0 and we have detected H1. So these are two different scenarios. And under hypothesis H1, that means that we have like there is the hypothesis H1, the signal is transmitted. When H1 is under the transmission, there can be two scenarios, that either we detect H0 or we detect H1. Okay, these are two classes. I'm making this in terms of two classes. However, when we consider it in terms of hypothesis, we can tell it as kind of we can like from the hypothesis perspective, it can be null hypothesis and alternate hypothesis. The idea remains the same. Okay, all right. So transmitted H0 is transmitted. What does it mean? That means no signal was transmitted, because hypothesis H0 is the null hypothesis, and H1 is transmitted means that the signal was transmitted. Okay, because this comes under alternate hypothesis. Now, the product of this prior and conditional probability, we denote it by specific expression. This is the notation. Okay, This is the notation. This is just for the sake of comfort, nothing else. Here R is the random variable, small r, and this particular R is that one particular instance. Okay, where we have transmitted H naught and detected H naught. Let us denote this by C00. Okay, so this is the probability under this particular instance where the cost is defined as C00. Okay, likewise we have four costs: C10, C01, and C11. Please understand, these are the costs associated with all these scenarios. Okay, so C00 is when 0 was sent and 0 was detected. C10 is when 0 was sent and 1 was detected. C01 is when 1 is sent and 0 is detected. And C11 is when 1 is sent and 1 is detected. Okay. So by by a very general guess, you must be able to understand that C00 and C11, the value of this would be relatively lesser than the value of C10 and C01, because we want to attach a higher price to incurring this loss. What price we want to attach should be in the context of that specific problem. Okay, the more sensitive we want a detector to be in that particular circumstance, the higher cost we should attach to the wrong decisions. Okay, in that way the detector would be more sensitive to not making incorrect decisions. Okay, it would be biased towards making correct decisions rather. All right, having said that, and having having set up this scenario, what we want to do now is all the scenarios of detection that we have. This is an instance. Okay, you must remember that we are defining the entire product of prior and conditional probability like this. We are trying to define it under a particular instance. Okay, the instance here is the cost, because we are trying to make it a function of the cost, this particular expression of probability. Why so? Because under all the circumstances, now we would be deciding an average cost. Now this would be our specific function. When we incorporate all the scenarios of detection and we take its average cost, that is where the key lies. Okay, if we minimize the average cost, we would be coming up with a situation where we would have a decision criteria. This is a very simple idea here. Okay, so for all the scenarios of detection, if there are respective costs attached to it, so the average we can take as summation of, because these are discrete quantities, summation of Cij and PR of Cij. You know this, right? X into P of X integration is the expected value of that, is the average value of that. You can talk it like this. In discrete terminology, this is summation. Why are there two summations here? Because we are taking two variables, as simple as that. So if we just expand it, you will get simply C00. This is for I and j to be 0, and this will be PR C00. So PR C00 is P naught into detected H naught and given transmitted H naught. Okay, this is the first condition. Plus, now we have C10. We are keeping the j constant varying I, and then we'll vary I and we'll vary j and keep I constant. This is how we shall expand it. So when we have 10 here, so it will be PR. So the summation would be like this now: C00 PR C00 plus C01 sorry, C10 PR C10, so and so on, right? So C10 PR C10 would be C10 into PR C10 is P naught into detected H1 given transmitted H0, plus, now we are done with keeping j constant. Now keeping j is equal to 0, now we will be doing j is equal to 1. So this will be 0 1 first. So when we have 0 1, PR of C01 would be P1 of detected H0 and transmitted H1, plus the last one we have C11. Now when we have C11 and PR C11 is P1 into detected H1 given transmitted H1. Okay, all right. Now that we have this particular expression, this is our average cost that we have. Now, if you put a little attention to detail, can you actually see that this particular expression that we have defined can actually be represented in terms of integration? For example, if we have uh, the signal transmitted H naught and also detected H naught, can we not write it as integration of PR H naught R dr under the region Z naught? Can we not write this? See, this comes from the previous lecture. If you remember, we have described certain scenario, we have described a particular scenario, particular phase, and then kind of for a particular threshold we said that this area belongs to something, this region belongs to something. We have defined it like this, right? So under, for example, these are the two hypotheses that we have. So under this particular the under hypothesis H naught, for example, this is the probability. So in the region Z naught, so for example, this is the threshold. So this is Z naught and this is Z1 for let's say. So this particular region is the particular thing that we are trying to see here. Okay. In a very similar way, if we want to find out this, so what would be when we are transmitting H naught and detecting H1, what would we get? This will be under Z1, and because we are transmitting H naught, the probability distribution would be under hypothesis H naught. Okay, RDR. Similarly, the this transmitted, when it is transmitted H1, the integration can be written as under the hypothesis H1, and because it is detected to be H0, so the region would be under hypothesis H0 Z. So because the detected is under hypothesis H0, the region would be Z0. Okay, this is something that we have described in the previous lectures in much detail with a visual diagram. Now I shall be putting it straight like this. Okay, I think there should be no trouble in understanding why this is like this. Under, see, when we are transmitting something, we are transmitting hypothesis H naught. That means the PDF that we have should be under hypothesis H naught, and because we are detecting something, that means it must have come under the observation region Z1. So that is all we are doing. Okay, our main intent is to transform it into a standard form, into a standard notation that has integrals. This second bracket notation is something that we have kind of invented for a particular purpose, but the meaning we assign to this mathematically. For this to be mathematically for us to perform operation onto this mathematically, it is very necessary that we transform into the proper mathematical context, and this is how it is. So I shall be finalizing this expression. Okay. So now, because this is the average cost and we intend to minimize this average cost, this is also called as base risk. Okay. Base risk is the expression that is used because this is the average cost. This is our entire thing upon which we shall be making decision. On minimizing, we would have some particular statement that would be our decision criteria. That will be our decision boundary that we'll be getting. Okay. So finally, this turns out to be C00 P naught under Z naught are given H naught RDR plus C10 P0 Z1 P are given H1 RDR plus C10 P1 under Z naught P of R given H1 RDR plus C11 P1 integration of Z1 P of R given H1 RDR. Okay. So I think this is very clearly understood why this is. Okay, this directly comes from the Bayes theorem. So we are using the entire Bayes simply because we can accredit this entire technology to Bayes. Okay, this technology of us finding the risk here like this, because this makes things a lot easier when we are given the relevant data. Okay, so what we would do in the next lecture is we would try to operate on this expression, because this is all that we have got. To minimize it, we need to differentiate it and set it to 0. We should do all that operations, all that mathematical notopoto in the next lecture. Okay, this lecture was primarily for introducing to you the idea of why uh, uh, Bayes needs to be Thomas Bayes needs to be called upon to solve this particular problem. Why? Because we have a little more information. We can make a little complex detector with little more information. The more information we have access to, the better guesswork we can do. That's all about it. Okay, that's all about the Bayes decision criteria. In the next lecture, it will be very clear why we developed this entire mathematics. I think in this lecture, I have been intuitively able to make you clear why this is so. In the next lecture, you will be seeing that manifesting into uh, a very standard notation that you have known all along this lecture series. Okay, so this is all about it today. Let's meet in the next lecture where we complete this part and try to solve some problems. If you have any kind of doubt, please don't hesitate to comment down below. I'll be more than happy and more than willing to help. Okay, because as I try to explain to you the concepts of this course, this is an exercise for me as well to check my conceptual clarity and to check my understanding on this subject as well. There are things that I may have skipped. If you feel that you have not understood something, please feel free to comment. Okay, and I shall respond as quickly as I can. So that's about it for today. Thank you for being with me in this lecture. Let's meet in the next. Thank you.